Shall we start?
Yes, please.
Yes, we have 10 minutes or something like that. Yes, exactly 10 minutes or
Yeah,
something.
already 10 minutes. Yeah,
Okay,
please go ahead.
we will talk about in the part 2 of the lecture, we can say part 2, we will have elasticity problems.
Mhm.
So we covered until now basics one-dimensional problem. We covered potential problems in 2 dimension. It might be in 3 dimensions. The same mathematics is not a problem at all. And now we want to cover elasticity problem. What is the difference between elasticity problems and potential problem? In elasticity problems, we have is not a scalar problem. Is not a scalar problem. Okay. In elasticity problems, for example, we will have indices. We will have indices. This is mainly because in potential problem, when we have our domain like that, we can choose any point here xi, and inside this xi we can have single source. Like if we have temperature or something like that, xi looks very bad. So this is xi. We have temperature, unit temperature or something like this. But in elasticity problems, we could have inside this point xi, we could have unit load in this direction, and we could have unit load in this direction if we talk about 2 dimension. So we have 2 directions for the load. For potential problem, if this is elasticity, and this is potential, in potential problem, we have a scalar problem. So we have u asterisk of xi and x is a single valued, is a number or something like that. So the effect from this point to this point x, for example, we have only single value. But now we could have inside this point x, practically we have 4 values. When we have our load, I'm going to put it in black here, in this direction, we will have effect here in this direction and this direction. Okay, when we have this value of the load, I'm going to put it in red, this one, this case, so we could have another effect in these directions. So actually we have 2 sources in 2 dimensions. We have 2 sources in 2 dimensions. Okay, and we have in the observation point or the field point, we have 2 values for each case. So now we are going to define our fundamental solution using not only 2 points xi and x, we will define it as with 2 indices, I and j, or alpha and beta. Let me put it I and j is not problem. Here, the first index, we are going to give it as a direction of the load. This is the direction of the load at xi. And j is the direction of the displacement. This is a displacement now. Before u asterisk in potential problem is the potential. But now u asterisk here is the displacement. The displacement direction at the field point x. And you have to bear in your mind that you might open a paper or something like that, you find alternative description of these two indices. This is very common in boundary elements. So when you read a paper or something like that, you have to know this author notation. This author notation means the first index is the direction of the load point or the direction of the displacement as a field point. Okay, so when I define U asterisk ij, U asterisk ij of xi and x, it is the fundamental solution of the displacement, or it is the 2-point fundamental solution, or it is the free space green function. Of the displacement. Why 2-point? Because we have xi and x. It is defined also, it is the displacement in the direction j at point or at the field point x due to unit load. Actually it is pulse load. Pulse is not right. Pulse, I can't remember the name of pulse load. Pulse, I think like this, I'm not sure. Pulse load at point, which is source point xi. This definition is very, very important. This definition is very, very important. In elasticity, you have to believe me now, U asterisk ij of x and xi equal to 1 over 8 by g 1 minus mu. I'm going to define every term. Minus 3 minus 4 mu ln r delta alpha beta plus r comma alpha r comma beta. Here pi is known, g is the modulus of rigidity. It is equal to e over 2 plus times 1 minus plus mu. Mu is Poisson ratio, and this is Poisson ratio. This is the Kronecker delta. R is one between the 2 points. This fundamental solution, it is named on Kelvin, Lord Kelvin fundamental solution. Lord Kelvin, actually his name is William Thomson. His name is William Thomson, and it seems before in England they change his name when they give him the Lord name. So he's Lord Kelvin, or his name is William Thomson. And actually, William Thomson is the one who put a lot of stuff in heat in physics or something like that. And before discovering the quantum mechanics and relativity, he said that physics is ended. We have no more physics. And actually now we have more and more physics after he said these words. So this is the fundamental solution of elasticity problems.